You ever stop and think about how your fitness tracker just knows you're running? Or how a tiny smart camera can spot a face in a crowd? Well, the magic isn't happening in some giant, far-off data center anymore. Nope, it's happening right there, on a little chip smaller than your fingernail. So let's dive into this wild world of tiny, powerful brains. Right? I mean, that's the big question, isn't it? We're talking about taking these incredibly complex AI models, the kind that used to need rooms full of servers, and shrinking them down to run on teeny tiny low-power hardware. It sounds totally impossible, but it is the absolute key to making everything around us smarter. For the longest time, AI lived up in the cloud. You know the drill. Your phone sends a question to a massive server, that server does all the heavy thinking, and then sends the answer back. But that's all changing. We are in the middle of a huge shift to something called Edge AI, or as the cool kids call it, tiny machine learning. And this comparison just nails it. Think about it. Cloud AI is like this giant central library. It has all the information in the world, for sure, but you gotta travel there, over the internet, every single time you need something. It can be slow, and you always need a connection. But Edge AI? That's like having the perfect little specialized guidebook right in your pocket. It's instant, it's private, because your data never even leaves your device. And it's incredibly efficient with battery life. Okay, so how in the world is this shrinking act even possible? AI models, these neural networks, they are notoriously huge, built from millions, sometimes billions of parameters. And then you have these microcontrollers, the chips that run our everyday gadgets, and they have almost no memory. You need some kind of bridge, a digital shrink ray, if you will. And that's exactly where tools like Xcube AI come into play. Just think of it as a universal translator and a super smart efficiency expert all rolled into one. A developer can take their big, powerful, pre-trained AI model and just feed it into this tool. Xcube AI then works its magic, crunching and converting that huge model into super compact, highly optimized C code that a tiny little microcontroller can actually understand and run. So what you're seeing here is the actual workflow. On the left, a developer puts in their pre-trained model, that's the brain. The Xcube AI engine takes over, sucks it in, runs it through the C code generator and optimizer, and then, boom, out the other side pops this beautiful, lightweight little library, all ready to be loaded onto a tiny chip. It's basically a factory for mass-producing tiny little brains. But, sometimes even with the best shrink ray on the planet, things are still a really tight fit. So let's look at a real-world problem an engineer could run into. They've done everything right, they've optimized their model, they're ready to go, and then they hit a wall. A memory wall. So this specific chip, the STM32H747i, it's a real workhorse. It actually has two brains, or cores, a super powerful Cortex-M7 and a more efficient Cortex-M4. It's got 2 megabytes of flash memory to store its programming, but here's the catch. By default, the chip splits that memory right down the middle, 1 megabyte for the M7 and 1 for the M4. And our AI model, it needs to run on that powerful M7 core. And this chart just lays the problem out bare. The space we have on that M7 core is 1,024 kilobytes. But our AI model, even after all that optimization, is still 1,200 kilobytes. It just won't fit. The program's going to throw an error, and the whole project is basically dead in the water. So what do you do now? Well, you don't go out and buy a bigger chip. You get smarter. Instead of just accepting that default layout, a clever developer can become a kind of digital city planner and literally rezone the memory map of the chip itself. And here is the city planner's brilliant new map. Just look at this. Before, it was a 50-50 split. The developer realizes, hey, that M4 core isn't really doing much in this project anyway. So they reallocate the space, they take almost all of the M4's memory and just give it to the M7. So now the M7 has this huge 1,984 kilobyte space, and the M4 is left with just enough to get by. Problem solved. It's genius. Now, this isn't as simple as flipping a switch. It's a really careful 3-step process. First, they have to change the chip's boot addresses. That's kind of like changing the street signs for where each core lives. Second, they have to update the project's linker script, which is basically the master blueprint that tells the software where to put everything. And finally, of course, they have to load it all up and test to make sure the whole system is still stable. And this isn't just some abstract theory. This quote, it's pulled right from the official technical manual. This is the actual line of code a developer would change in that blueprint file. They are literally telling the compiler, hey, listen up. The memory for this core, it's not 1024K anymore.
Its length is now 1984K. It is a tiny, tiny change with a massive impact.
So we just went super deep into a really specific technical little fix, a single line of code in a single file. But it's time to zoom back out and really appreciate why this kind of detail is just so incredibly important.
Because this is it. This is the invisible work, the clever engineering that makes our entire modern world tick. Every single smart device you own, from your phone to your car to your coffee maker, it's all built on a foundation of thousands of these tiny, clever, problem-solving decisions made by engineers. It's all about squeezing every last drop of performance out of the hardware we have. Innovations like this mean that the barriers to putting real intelligence into everyday things are just falling away. We can now put a brain not just in your watch, but in your shoes, your water bottle, or even in the soil of a farm field. So the question is no longer if we can make something smart, it's what should we make smart next? And what is that future even going to look like?